right. I hope that you all are doing well. I hope that your homework is going well so far and you're learning a lot from the class. I hope that it's at least going better than my League of Legends rank right now. Anyways, let's see. Business Calculus 1.6, we're on to the natural logarithm. All right. A lot of people have feel uncomfortable working with logarithms, and that's fine. But we do need to know some things about them in order to work a lot of problems in this class. We need to know the basic idea and just, the basic techniques for solving equations with logarithms. And we should know why we need logarithms. All right, so let's get started. So first of all, consider an equation like this. Y equals x to the fifth. Okay, y equals x to the fifth. So I guess this would be a quintic function, and we can immediately solve this function for x. We can do that by just taking the fifth root of both sides. And remember that when we take an odd power root, I won't draw the actual radicand here, but this means take the fifth root. When we take an odd root, we don't need to write plus or minus because only the positive root will actually be a solution. So we don't have to worry about writing a plus or minus. In fact, if you write the minus, it's wrong, because that negative to an odd power will be a negative, and there is no negative over here. Whereas for even roots, a negative 1 times an even power will be a positive, which is what we originally had over here. So just remember that. Don't need the negative for an odd root. So you can solve for it. The whole point is, the idea is that you can solve for x. All right, really quickly. And these are the same formulas written differently. Y equals x to the fifth, or y to the 1/5 equals x. It's the same equation, just written differently. And the difference is really in how we're thinking about it. When we write the equation like this, we're thinking of y as being a function of x. In other words, if we have x, we plug it in and get y. Whereas when we write the same equation differently, we write it like this, we're thinking of x as being a function of y. So if we have y, then we can plug that in and get x, right? We need to be able to get either one. Whichever one we have, we need to be able to get the other one. All right, so that's the difference. So I wrote, normally you don't see it written like this, but I went ahead and wrote it out, y of x as a function of x, and x as a function of y. All right, so this process of reversing the roles of like which variable is the independent variable and which variable is the dependent variable, this is called taking the inverse. And it's possible whenever you can always take an inverse whenever you have a function that, for example, satisfies the horizontal line test, which you may have heard about. So that means that a horizontal line shouldn't pass through more than one point on a graph. Okay. Anyways, that said. All right, so that's how to take the inverse of a function y equals x to the fifth. Now, let's switch it slightly. Instead of x to the fifth, now we have 5 to the x. All right, so now what I've done is, instead of writing the variable on the base and raising it to some number, now I have some number and I'm raising it to the variable. All right, so I switched it up slightly. And now if I want to solve this equation for x, I can't do the same process, which we wouldn't expect to be able to do the same process as before. And in fact, there's not that much that I can do. I can't like divide by 5, that doesn't help. Taking roots doesn't help. Subtracting by 5 or something, or dividing by x, none of that's going to help. All right, so what we need are logarithms. That's the whole point of logarithms. If you never knew the reason for logarithms before, the reason we need logarithms is to solve equations where the variable is the exponent. And in fact, the logarithm is exactly defined as the function that solves for that exponent. All right, that's how we define it. We say there's a we know there's a function. We figure out there has to be a function that solves for that exponent using math stuff, and then we say, okay, we'll call that function the logarithm. Why do they call it the logarithm? I have no idea. But anyway, that's what they do. All right. This is how to compute the inverse of an exponential function. All right. So if you have b to the x equals c, a logarithm will solve for that exponent. That is a variable. That's the whole point. That's the whole point. Okay. Now, we will only need the natural logarithm. This is the logarithm of base e. We say it's base e. This e as a subscript here, that is Euler's number, approximately 2.72 that we learned about a little bit about in the last video. Euler's number, there's a lot to be said about it, but we don't need to talk about all of that. If you're interested, you should check out the Wikipedia article or something. It's an interesting number. It comes up all over the place. But for us, all we need right now is we need to know, all right, the function that we're going to need is called ln, natural log. And it doesn't make sense on its own. It needs an argument, which here is x. Okay, this is the function this is the inverse of the function e to the x. All right, we're going to need to use this to solve lots of equations in this class, and so you'll get, it's not that hard, but you just need to learn the process. So here's some facts about working with logs that you should keep in mind. First of all, ln of e to the x is just x. It sort of, quote, cancels it out, the ln and the e, kind of. You can think about it like that, it's okay. But yeah, ln of e to any power, it will just be that power. All right. Ln of e, that's 1. Why is that 1? It's because log actually asks for the exponent. It gives the exponent that you need to raise the base to. See how b is the base in both cases? It's the base. That's why I use b for base, that you raise x to get whatever this is. And ln of e, so that's saying what exponent do I need to raise e to get e? 1, because e to the 1 is e. So that's why ln of e is 1. Why is ln of 1 0? Because it's asking, this is asking for the exponent that you need to raise e to get 1. What exponent do you raise e to get 1? The power of 0. Anything to the power of 0, it's 1. So that is also true in the case of e, because e is a number. All right? So ln of 1 is 0, ln of e is 1, ln of e to the x is just x. All right, good. That's good. So, for example, maybe we have y equals 5 to the x. This was our original problem. And if we want to solve this for x, we'll basically always use this process, this technique. We will take log of both sides, or take ln of both sides, like this. We will just write ln. Okay, so we'll write an ln next to both of these things. And now a property of logarithms allows us to take the exponent and move it out in front of the logarithm, right here. Okay, so whatever exponent this is, whatever the exponent is, maybe it's two numbers, maybe it's like x times k or something like that. Well, they would both be brought out in front, and they would be multiplied. Okay, so whatever is here, it gets moved out in front and multiplies times the log. Now, at this point, we have, on the right-hand side, x times a number. ln of 5, that's just a number. Don't think of this right here as a variable. It's not, it's just a number. Imagine it was the number like 2 or something like that. All right? If you had 2 times x, how would you solve for x? You would divide by 2, right? We do the same thing here. So we have ln of 5. We'll just divide by ln of 5 on both sides. And that leaves just x on the right-hand side. All right, so this process, this technique, allows us to solve for x. And we did that using logarithms. And in particular, we used the natural logarithm. Why did they define it as ln to mean natural logarithm? Why not nl? Maybe you can tell me that. I have no idea. Another one of those things that I have no idea about. But I know how to use it So that's what I'm teaching you. Why did we put the decimal here? It should be here. Whoever wrote the presentation, that was, yeah, big mistake there. Oh yeah, it was me. Oops. Okay. All right. So let's move on. So we talked about how logarithms are the inverse of exponential formulas. Okay. And the natural log, that's the inverse of the exponential function y equals e to the x. All right. If we solve the function y equals e to the x for x, we should get the natural log function. All right. So we'll use the same process that we used in the previous slide. So we'll take ln of both sides. We took ln of both sides. And I do the same thing as I did before. I bring this exponent out in front. It's just a property about logarithms. It's just true for any number x and any number e here. And then we have x times ln of e. What's ln of e again? Ln of e is 1. Ln of e is 1. So we just have this number x times 1 here. Well, x times 1, that's just x. So already we have solved for x. X is ln of y. Okay. Here's what these functions look like. To compare them side by side, here's the exponential formula, e to the x. And here's the natural log function, ln of x. Notice that, is this function positive or negative? It is positive. It lies above the x-axis. Is it increasing or decreasing? It's increasing because it's going up from left to right. Is it concave up or concave down? It is, let's see, concave up or concave down? It looks like part of a cup shape. So it's up like a cup, it's concave up. Okay. How about ln of x? Is it a positive or negative function? Well, down here, for x between 0 and 1, it's a negative function. It's below the x-axis. And then after that, for x values greater than 1, it is a positive function. Is it increasing or decreasing? It is increasing, just like e to the x, also increasing. It's going up from left to right. Even when it's negative, it's still going up. How about concave up or concave down? This is part of a frown shape. So this is concave down. Concave down. All right? So that's that. Okay, good. Let's move on. All right, this is something that I've said and I've used a couple times already, but I just want you to see the formula. Ln of a to the b, that's b times ln of a. In other words, this exponent just comes out in front. All right, you're always allowed to do that. Or you can, if you have this situation, you can move it to the exponent if you'd like to do that for some reason. All right, and so for example, let's say we have this equation here, 72 times 5 to the x, a little different than the one we had previously. And really, that difference is only the 72 right here. Remember not to multiply the 72 times the 5. You can't simplify that. They're not to the same power. So you can't bring that into the power of x or something like that. So if you're trying to solve for x, you can move this thing to the other side. Just divide by 72. So now all we're left with on the right-hand side is 5 to the x. We'll leave this as y over 72. And then we will take ln of both sides, like as we have done before. I'll make sure to put parentheses around the things that I'm taking ln of. So I'll put parentheses around y over 72. And now I can use that property of logarithms to bring that exponent out in front. So I'll have x times ln of 5. I haven't changed the left-hand side. All right, now I have x times a number. If I want to solve for x, I can just divide by that number. So I will divide by ln of 5. So x is this. It is ln of y over 72 divided by ln of 5. And that's about as far as we want to go in terms of simplification. We don't want to simplify it any further. There's not that much else you can do about it. Okay, just leave it like that. You can't, so you might think, I have ln of something over ln of something. Can I combine that to 1 ln? And actually you can't. So don't try to do that. Just leave it as it is. It's perfectly fine. If you keep simplifying, you're always in danger of simplifying incorrectly. But you can just leave it as it is, just like it is. All right, good. So that's that. And just for reference, that's basically all the rules that we need for logarithms, just this one here mainly. But in case it comes up later, I don't think it will, but you should just be aware that there are other rules of logarithms, like if we're multiplying two arguments together, then we can break that up into a sum of two logs. So I would say log of a product of two numbers is the sum of the logs. Log of a quotient, a over b, of two numbers will be the difference of their logarithms. You'll take their logarithms and then you will take the difference of those and we'll subtract. And then we talked about these three last ones here. So I don't think that these middle two will come into play, but who knows? Who knows? So that is that. All right, let's move on. All right, so in the last video we talked about exponential functions, and I told you that there's two ways to write the exponential formula. And we just talked about the first way. We just talked about the annual percent way. So remember what exponential functions are. They're functions that change by a constant percent as you increase the x value by the same amount. Usually we consider that amount to be 1. All right, and we talked about how to get the rate, that growth rate, by taking the growth factor and just subtracting 1. Now we need we need to know the other way to write the exponential formula, and that's like this. It's like this. It's very similar. It still has p naught, which is the y-intercept. That's the value of the function p when t equals 0. We don't need to write parentheses. We just tuck that 0 in as a subscript. That's like the t being 0. And then we have e to the power of k times t. Remember to put k times t in parentheses anytime you use that. And here, k is the continuous percentage growth rate or decay rate. All right. So whenever you see the term continuous or continuously, then that's a tip that you're going to use this form. All right. You will. It's almost every time you need to use this, you'll see the word continuously and vice versa. All right. So keep kind of identify e with the word continuously. All right. Keep that in mind. That might help. All right. So this continuous percent change, it's a little bit different. It's a little bit more. It kind of represents a little bit more than this r here. All right. How are the k and the r related? They are related. Basically, this r, this is the rate that's added on at the end of a year, whereas k, this is kind of the amount. It's called an annual percentage continuous rate, so it's kind of the amount after a year, but it's a little bit more because you accumulate some a portion of that percent in each moment along that year, right? So what's happening is the interest that you're earning over the course of the year, that starts earning a little bit of interest. So what you end up with is something that's a little bit more than if you just added on a percentage at the end of the year. You get a portion of that interest or whatever it is throughout the year, and then that portion that's added on starts earning interest after it's added on. Okay, so for example, this will give you a way to see that they're very similar in the way that the formulas are written. Notice that if we put that a is actually e to the k. I could substitute a in here for e to the k, and that would be a to the t here. All right, so a is e to the k. So if you want to go between those, this formula will help you do that. K is the variable. If you think of k as a variable here, we could take logarithms of both sides and solve for that. And so if we knew a, we could get k. All right, so forget that for a moment. So for example, let's say you have a continuous rate of 15%, which when we write the value of k, normally we write that as a decimal. And so a equals e to the k, e to the 0.15, that's 1.162. Well, a growth factor of 1.162, remember that's 1 plus the rate. So if I subtract 1 off of that, I get the rate, which is 0.162, which is 16.2%. All right, so it's a little bit more than, it represents a k of 15%, will give you a little bit more than it would if when it's compounded continuously, as opposed to being compounded just once a year. I said that before, I'm just reiterating. Okay, so that's that. And notice that when k is a positive number, we have exponential growth. K could also be negative. That would be a negative rate, and that would be decay, just like before. This is the same as for r. When this rate is positive, we have growth, and when that r is negative, it's decay, which is what less than 0 means. All right, so that's that. Let's move on. We have another example here. It's the last example. All right, suppose we have a function that gives us the number of deer in a park, and that function is this right here. It's p of t equals 4,000 e to the negative 0.06 t. And so p is measured in deer, it's the number of deer, and t is the year since 2000. Just as a little note here, this is a very common way to define time, and it's a little bit different, I think, than we've seen previously. Notice the subtle difference. It says years since 2010. This means that t equals 0 corresponds to the end of 2010. So if t is 0.1, that would be a little bit of the ways into 2011. That would be like early February 2011. All right, this is a very common way to define the time. So keep that in mind when you're working the problems, that you pay attention to how t is defined. All right, so here's the solution all at once. I could put a few more breaks in here, but I hope you're okay with that. So in any case, you don't have a choice. All right, in 2015, so let's see, can we figure out how many deer were in the park in 2015? Well, 2015, that's 5 years after 2010. So I can just plug in 5 for t. I make sure to put this in parentheses when I enter it in my calculator. When I write it down on paper, I don't need to use parentheses, but the calculator needs that. Otherwise, it will find this and then multiply that by 5, and we don't want that. We want it to do this first and then raise e to that power. Okay. Anyways, we get this number. And we'll just round that to the nearest whole number. So that's about 2,963. That was tough. 2,963 deer. We measure deer in deer. All right. When were there 2,000 deer? Okay, so this is the other way that we could ask the question. Instead of giving the x value and asking the y value, we might ask for the x value and give you the y value. So now we know the y value, so we'll plug that in for the left side of the equation. And we'll just copy down the right-hand side as it is. Now I want to divide by 4,000. This is really the only way to go. Do not take logs at this point. We do not want to do that. No, 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 no. Although it's okay if you know what you're doing, it makes the problem longer. So first we want to divide by 4,000. So after I divide 2,000 by 4,000, that's a half. And then the right hand side, we have this left. Okay. Now I have a situation where I have an exponent that I need to bring down, and so I take log of both sides. I take ln of both sides. So I write ln, and make sure that I have parentheses around my 1/2. All right. And let's see. Oh, remember that ln of e to the x? Remember that's x, right? Well, in this case, we have ln of e to the x, where x is negative 0.06t. All right, so this just comes down, negative 0.06t. The ln of e is just 1, so that's all that's left there. And then the last step is very easy. So we just have a number times t, and we will solve for t by just dividing by that number. And I'll switch the order. I'll switch the right-hand side and left-hand side for the final step. T is ln of a half over negative 0.06. Make sure you're using the negative key when you're entering this into the calculator and not the minus key. Okay, and when we solve that, when we put this into the calculator initially, it looks like maybe we'll get a negative number, which is kind of concerning, because a negative time, usually that doesn't really make sense. But ln of a half is a negative number itself, so when we divide by another negative number, we get a positive number. And we get 11.55. And that is t, which is defined as years since 2000. Now remember, t being 0, that's like at the end of 2000. So 11 years after 2010, that would be like at the end of 2021. 11 would be at the end of 2021. So another 0.55 years, that would be like another 6 months. That would be about halfway into 2022. All right, so let that sink in a little bit, because that'll definitely come up from time to time. Time is, there's a pun in there somewhere. Anyways, all right, so we made it. That was kind of a tough section. I hope that something made sense about logarithms for you that didn't make sense before. And good luck with your Wiley Plus homework, and let me know how it goes. All right, have a good day. Goodbye.